Thank you. Thanks for coming. Thanks for inviting me. I'd like to start with a philosophical perspective about virtual reality and the digital world. I was inspired by this French philosopher, Jean Baudrillard, that I like the definition of hyperreal in the world we are living, and particularly in the digital age, more real than real. And this is, I think, very important in relation to, hopefully, our final discussion, how we interpret what we see, how, which processes. I'm particularly, I found particularly important to see in the history of the humanities archaeology, a place for archaeology at the forefront of digital technology. I know that perhaps this is not maybe so clear, so understandable for several media, with the romantic idea of archaeology, which is not hyper-technological, but this world is different today. And in my presentation, I'd like to distinguish or take care of three different worlds, and I call digital minds, human brain, artificial intelligence, and see if it's possible to connect them by computing and visualization. First of all, we need a quick summary of visualization technologies in the past 30 years or so. And I'm trying to help the audience to see, for example, some definition, which actually now part of our scholarship. So virtual archaeology in the 90s, cyberarchaeology 2008 because of the theoretical archaeology workshop organized at Stanford, and that's the very beginning of the School on Thinking, and perhaps artificial intelligent archaeology later on. So the question is, again, if we connect virtual archaeology, digital archaeology, neuroscience, artificial intelligence, what we see in common, what they have in common? Well, I think the simulation for understanding and modeling complex systems. And this connects us with the second cybernetics. So we have an idea, hopefully, about the theoretical background of this definition and also at least my approach. Well, I was inspired by Gregory Bateson and other scholars in the second cybernetics, and particularly I like to emphasize the fact that in the second cybernetics, the observer is part of the system. So it is object and subject of observation. And that's why I believe the cyberarchaeology observes that in action, simulation, VR, 3D environment, but at the same time, they are part of the same system. Again, in this loop of observing and being part of observation. So that's why we see the past as multiple pasts because of this perspective. And the definition of digital mind is based on the evolution of virtual archaeology in cyberarchaeology, perhaps one day in AI-Archaeology, and reflect the relevance or the mechanics of interaction simulation performances versus the predetermined static reconstructive process. In order to give an example, in the 90s, in order to visualize a 3D model, it took weeks. We had, and then weeks and weeks of computational power. Now we can do it in real time, at least some of it can be real time. But what is interesting in the idea of digital mind is that computer simulation creates feedbacks, affordance, interaction, basically a new cycle of interpretation, which in my perspective is multi-model and creates a combination of questions and research questions that we actually discuss later on. So it's an endless cycle of digital computing. And this is related also to human embodiment and in action, because a visual model, and particularly in immersive VR, involve our human presence in that space. And this creates a different perspective in the interpretation process, spatial embodiment. So what happened? Well, I think if we are correct in the premise, so digital archaeology, or that digital archaeology, is at the intersection of digital memory and performance, where I briefly classify digital memory, documentation, fieldwork, data entry, and so on, in the performance, 3D modeling, interaction, embodiment, simulation, and action. Basically, when all the data set flow and create a different kind of knowledge. So we're talking about different forms of knowledge. So in order to, well, again, see this perspective in the research perspective, the last 30 years, I have to start with supercomputer, because my work started in a supercomputing center. And that was my PhD dissertation. So you know at least where I come from. And you see the size of a supercomputer in relation to a human, you know. And in order to produce something now we do with a mini computer, we use supercomputer. I have also something I like to share, because I'm in Chicago, and my first work of image processing was based on a software released at the National Center for Supercomputing Application, Illinois, Urbana. So this particularly is published. It was an automatic classification of an archaeological site by using a remote sensing algorithm delivered by that software. And you see this is in southern Italy. And I'm a particularly interesting case study, because at the time we had just a supercomputer available to do models, or perhaps to train algorithms. This book I have co-edited in 1996 was basically the very beginning, at least in my world, of determination of virtual archaeology as perhaps a discipline or research application, cool stuff for some authors. And I give you a very short chronological perspective of some work done in that period and beyond. So the Virtual Museum of the Scrovegni Chapel, I created in 2003 based on desktop virtual reality. No headset available at the time at all. In 2007, I started to work with virtual reality collaborative systems. So we start to ask ourselves how we can have different scholars or visitors in a museum. This is the Roman National Museum in Rome, together in the same space, playing like avatars in the Villa of Livia, disposed of the Emperor Augustus. Or later on, moving to United States, University of California, using Second Life, which was actually the first metaverse you might know in the digital world. And we're teaching classes actually in the virtualization of the same Villa of Livia, but available for a class of archaeologists in this case. Later on, 2009, first serious game based on the history and historical documents at Fort Ross in Northern California. When I start to work, sorry, I have to see if I'm connected to the internet here. Yes. We created a teleimmersive system in actually connecting the different university campuses together. This is something we should still think about, because after that pioneering experiment, nothing happened. So I couldn't continue that kind of research. But I'm very proud to say that teleimmersive environment was a very simple device, low cost, for having archaeologists around the same model from different campuses. So, and this, I think, and we're able, this is very primitive, you see 2009, 2011, and the virtualization of real person in a virtual environment like this. Okay, we are much closer now to our age. I started a 3D digging project at Chateau with Stanford University in this period, and with the idea to virtualize the archaeological excavation. So this was a very ambitious project related to archaeological fieldwork. You see that the stratigraphy were coming together as a virtual world, and browsing a stratigraphic unit is particularly important in order to regenerate a process like an excavation, which is very destructive, basically, when the excavation is over. And I use this simulation in the Duke immersive virtual environment, basically a cave. This cave, costing, if I'm not mistaken, $5 million at that time, was discontinued a few years later because it was an unsustainable model. In fact, now we have virtual reality headset, which costs a few $100s or so. But the point here is how to teach a class in a virtual reality environment. And we did this, particularly for grad students, and you see this is a discussion actually in the simulation environment. And you see that actually in the background is the Neolithic house. In 2017-18, we developed a system costing $150. I repeat, $150 for the Museum of Imperial Form. It is a prototype called Tangible Interactive Table for Archaeology, developed by collaboration between Duke University and North Carolina State. And the result of this is the virtual reconstruction of the frieze of weapons of the Basilica Ulpia in Rome. As you see, it's a tangible table, so basically we use haptic technologies in combination with visual technology together. I like to emphasize this product because it was done by us as a group of teachers and students for a museum. And this is an important museum. So I'd like to, it was really an interesting and important public outcome of the exhibition. As you see, the complexity of the frieze is like a puzzle, requires actually the recomposition, graphic recomposition, but also the use of 3D print. That's why it was a pioneering use of 3D, now well, not pioneering anymore, of the use of 3D print for connecting the visual with the tangible part of the archaeological artifact. And same for this, for the Basilica Ulpia, we developed, this is another master student app in augmented reality. You see the Forma Urbis Rome, which is actually the printed on the table. In augmented reality, the app was available for the general public, school, and so on during the exhibition for 1 year. For the same exhibition, we realized also this very interesting experiment of holographic projection. It's technically a photopolymer film, laser printed, using a full parallax. And actually, if you see, this is actually a very interesting digital analog product because it's digitally developed, but when you walk around, you see the hologram, you see different layers, actually, of the basilica. and we collaborate with this company, which is not on the market anymore, but it was a very important, I think, example of outcome in the case of digital production. This film is 1 millimeter of thickness, so this is important to know. The last example of 3D printing plus video warping projection is from another exhibition organized in Rome last year. As you can see here, this is actually the landscape of Vulci, which is a Etruscan Roman site in central Italy. And what we did here, we projected over the 3D print of that landscape. The landscape is generated by LiDAR data. So, okay, you have LiDAR data, print it out, and project the different, actually, aerial view maps, old maps, remote sensing data, and so on. This is was done for the University La Sapienza in Rome. So it's important that is available also after the exhibition for groups of students, visitors, and so on. As you can see, how actually the interpretation of the site comes from different sources, and that the landscape, too, has to be interpreted by different sources. So you can see that, for example, this is a multispectral visualization of the plateau, and where we can see different elements of the and structure of the Roman city. Okay, this is the introduction to the visualization of hidden landscapes, so how to use non-invasive technologies for producing digital data set. Again, this is exactly the site you have seen in the other videos. Vulci is, in this case, is a very large, over 30 hectares of archaeological remains. What we see here is a digital vision model plus LiDAR data, created by over 5,000 of digital photos by different sensors. So what we see as a unit is not, actually. It's a result of different digital processes. The importance to use non-invasive technology, particularly GeoRadar, was very successful here. I like to, again, to emphasize the importance of this kind of techniques, particularly GeoRadar or magnetometry, depends. In this case, magnetometry didn't succeed because of the noise coming from the volcanic soil, when we don't have the chance to extend excavation like in this case. You see, this is a Roman domus entirely visible, identifiable by GeoRadar. Or here we see about 7 hectares of GeoRadar prospection in the southern part of the plateau, or a combination of different technologies. In this case, we use digital photogrammetry for the monument, the monumental part of a late Roman building, and the identification of the Roman basilica in the underground by GeoRadar. So basically, the 3D pixel you see are recognizable, but not visible on the surface. This is the example published recently in the journal Field Archaeology, and again, always proud of the involvement of several grad students here. They work on the interpretation of this basilica, which is actually very recognizable in size and in shape. The other question about the underground was how can we deal with pipes, canalization, wells, cisterns, and so on that are underneath. So we are using, in this case, LiDAR scanners for the surface and geoelectric techniques for visualizing the presence of water underneath, which is particularly important in order to track the water and hydraulic system in the soil. In 2019, we developed a prototype of smart trowel, which is a multi-sensor device with different capacity to, basically, you can you can track and record digitally the movement of the trowel as well. You can draw on top of the soil. This is also a small sensor for georadar recording. Again, there's much more to be done here, but I think the use of nanotechnology and digital technology applied to sensor in the field is particularly appealing. The trowel is our tools in the daily life of the archaeologists. Again, the use of digital photogrammetry in this case documented and recorded entirely a Roman cistern. This is another example where digital photogrammetry can totally replace autoptic or empirical work, because if you are inside the cistern, you can't see anything. And if you are outside the cistern, you don't see the cistern. So the point is, how can connect the visible part, which is the building, Roman building, with a floor in travertine on the top with the cistern. So this was a way where you see the digital really functioning and saving time and in the recording process. Last but not least, the introduction of multispectral drones was very successful, and particularly in the summer, where all the fields look the same color, for example. And I like to emphasize the fact that the vegetation index, or in general, so the near-infrared part of the spectrum is the most interesting one. And in order to give you an example, this is the northern part of the site, so the same plateau you have seen in the first slide. And you can notice here all this kind of light, yellow light lines. They are all T-shaped tombs, so they're funerary chambers recognizable by multispectral. So basically in the summer, this is a grass field. So you will see green or yellow in RGB, in red, green, and blue, not anything else. Same here, we use the vegetation index, which is a calculation of humidity in the vegetation, and more recently, the application of LiDAR drones all over the plateau. You see that in this specific case, the Nake soil. We have a lot of examples, for example, from Central America or South America, but in our case was very important in order to penetrate all this vegetation, which covers part of the site. Another very effective and successful processing. See LiDAR, this is all vegetation here. If I use LiDAR, you can see at the bottom right, see actually here, see the dromoi, so the corridors to Etruscan chambers. All of them are under this area, but not visible otherwise. The final result, or semi-final result, was a dissertation, another PhD dissertation, and with the reconstruction of different phases of the city, and Etruscan and Roman particularly, visible by different sensors. So in other terms, we cannot trust one single sensor. We need to multiply actually the remote sensing capacity and generate an outline like that. So basically, it's a new knowledge of the site based on, again, non-invasive technology. On the right, you can see the tentative chronology. On the left, the tentative chronology. On the right, the different sensor use. Okay. In 2022, another PhD student developed an augmented, I would say a sort of augmented reality GIS app based on non-invasive technology. So you see the field in the video is completely empty. This is just grass. But actually, when you walk in, on top of this, you follow the result of the GPR, okay? And this is particularly important for visitors when they have a sense of emptiness of the landscape, and when they walk on a field like this, they cannot have any idea they are walking over a Roman basilica, a Roman domus, or an Etruscan building. But we can help them with that. So this is really a way to contextualize in the space. Basically, it's on a scale. You see a little dot, and when you follow that, you see your position and where you are when you walk into the field. This is done by any smartphone and available. At the very end, the procedural modeling with tentative reconstruction of the city. About excavation, as we did in Çatalhöyük, we virtualized the entire process. So basically, for us, virtual reality is a tool we use during the excavation, because this is something typically we see in other places, but not the excavation. It's important to use virtual reality in excavation because we can train students, but also diggers. After 1 year, they don't recall exactly what we have left, right, a year before. And then this is a way to go back virtually to the same archaeological phase, and then we start again. Or we need to we want to compare different phases. So all this kind of digital world that producing different ontologies, a different format, is now a publication, part of a digital publication process. In this case, we are using Morphosource as a 3D repository. This is developed at Duke University. Initially was developed for human fossils. Later on, is developed for cultural heritage. Fulcrum as a multimedia EPUB publication, and Mozilla Hub, a collaborative platform, as engagement layer. So the idea is this will be done by March, so hopefully you should be seeing the results soon, is to try a different form of publication, basically with a narrative, with text, but also with hypermedia link to other virtual worlds. If you want, you can take that set on and see in VR. If you don't, you can see it over the desktop, okay? And then we go to brains. So my last part of my presentation will be about the intersection between human brains and finally artificial intelligence. But first of all, I like to start with the first project named NeuroArtifact. Well, first of all, this is my brain. So there's no privacy here. This is me, okay? My brain. And I want just to explain what we look at, because otherwise, the experiment seems interesting or perhaps not interesting, but we need to understand why we care about waves. So the project I'm going to present combine EEG, electroencephalogram, and eye tracking. Okay, so the electrical activity is actually divided in theta, alpha, beta, and gamma waves. As you can read here, every single frequency is associated to different mental activity. I don't want to simplify this or overestimate this, but this is what we have to know when we start to evaluate cognitive impact, cognitive workload, emotional index, and so on. And this is the project. So the first experiment was done on site. This is the eye tracking during the archaeological excavation. And during the pandemic, I asked a group of 20 students to be virtually engaged in immersive reality, virtual reality, and using eye tracking. So in order to see how a group of archaeology versus group non-archaeology was watching and perceiving the excavation. This was a very tentative experiment. When we had a scientific protocol in place, we started a 1-year project at the National Etruscan Museum of Rome. So if you we'll see how museum can be involved in this process. Our case study is the following. As you know, I'm originally an archaeologist, so my background is particularly pre-Roman Etruscan archaeology. This is perhaps one of the most important artifacts preserved in a European museum, and this is the sarcophagus of Desposis. Okay, the research question here was to evaluate the neurostatic experience in virtual reality of this artifact and the same artifact in the museum where you can see there is a specific room dedicated to that. The museum is the number one in Europe for Etruscan archaeology, so we established a scientific agreement between the University Sapienza in Rome, the museum, and Duke University. And there are several research questions here. You will see that at the end we have some preliminary result, and we do not yet pretend to answer all the questions, but it's interesting to start with some. First of all, spatial embodiment. You know, we have a different spatial embodiment if we are in empirical reality or we are in virtual reality. And this is important, not because of the experiment itself, but because if we know the process, we know how to change the learning process, how to accelerate the learning, and one day perhaps how we can speed up and adapt the learning to different categories of people, for example. So it's not just about archaeology in my point of view. So in this case, the model was initially scanned digitally and later on implemented for Unity 3D. So what you see now is a lighter model. And the eye tracking is important because of the region of visual interest, visual dwell time with visual region of interest, so we call fixations, technically, and frequency of saccades and fixation throughout the experience. What we observe is not a simple activity of watching. We think, and that's why the human perception is a multimodal activity. This is a map of temporal, frontal, parietal, a brain lobe, and the electrode associated to them. When we work with EEG devices, we can have portable system. So that's why the museum experience was successful, because we could work with a very portable system. And then biometric data. So you see that the combination of biometric data makes sense if we know what we watch, how long. And here are some big questions and behind this, particularly in line with hopefully future experiment. The study of the ancient mind, so the creational process of the artist. Who made the sarcophagus? What is that perspective? The interaction, which is ancient and modern too, so which is a consumption. Every artifact has a consumption. That's why we create affordances between us and an object. Then the visitor experience. What do they see? What do they learn? How is this process? And then the embodiment, of course. The second step is, again, biometric analysis. So we need to combine different sensors. This is the EEG recorder. It's called a Revive. And we use a shimmer, which is galvanic conductor, we'll say the sensor, which is actually over the user hand. And we can measure here also the emotional state. In other terms, cognitive and emotional processes, neurometric, synthetic indexes that summarize information regarding the mental state of users, and then other application, combining the shimmer, 2 electrodes on the skin, see the GSR and heart rate. There are more sophisticated shimmer, of course, that use in other fields. But this is important because of the combination of biometric data we collect at the same time. The neurometrics adopted in the current study, so attention, so this is important because there are metrics for each single element of the protocol, so observation and active task execution. Watching is part of the task execution as well. So attention indicates the level of each participant during the performing, which is 60 seconds for each experiment. Workload, cognitive workload, how demanding a task is, so how much we are engaged with a task, and emotional index, in this case, the emotional involvement toward a specific stimulus. In the field, or in the museum in this case, we collected simultaneously, see the device, actually this visitor has the electrodes in the shimmer, and this smartphone is actually the connector to the eye tracker. So you have actually glasses very similar to normal glasses connected with the smartphone in order to have eye tracking and recording. And this is actually sort of summary, visual summary. So EEG, electroencephalogram, eye track in the middle, and virtual reality. So the experience in the museum, the experience in virtual reality, and so on. Research question, is the experience in the museum and in VR different? Very likely yes, but how is different? Why is this different? And is there any difference between category groups or categories of people visiting the museum first and later the labs and so on? And then can we categorize them one day? But that's not about biometry or biometric recording. It's also about experience. And then we see here a questionnaire based on neurological, neuroscientific literature where you see the questions and actually the option for the survey. In this specific case, this is the analysis of the emotional index, so the workload, 7 users in the lab, 18 users in the museum. You can see here actually the museum in green and the lab in red and the workload. So everything is, of course, including the emotional index in favor of the empirical experience. So people in the museum have a different kind of engagement, of course. It's somehow expectable, but the fact that we can quantify the neuroaesthetic experience is I think, very important. And this is, finally, it's about one individual. The correlation between observation, you see the green dot, actually the region of interest, observation, and the workload, and the attention and the emotional index here. You see that they're non-stable because every second or cluster of second, the experience is different for this individual in the cognitive workload, the attention, and the emotional index. Particularly interesting here because at some point, the cognitive workload is lower, but the attention is higher, and so on. So this give us a little bit of sense of the complexity of the aesthetic experience towards a real artifact. You can multiply this for hundreds or thousands of visitors, you can understand what's going on, at least in part, in the human brain. Unfortunately, we don't have a literature about this. So I hope that we can, in the future, engage more museums and more experiments, having also different questions, because what we have is based on what was possible and sustainable to do with a small group of students, and all volunteering to do that in a public museum. I have to say that the museum director was particularly pleased by the result. So the question at the end, and we have more to process, so it's a work in progress, it's main region of interest, how long, mental state, differences between gender or similar profiles, background, skills, and so on. We're talking about people, subjects that have different training, different background, and so on. See here, this is particularly exciting to me image because it's the result of cumulative observation. Basically, this sarcophagus is generated by eye tracking. It doesn't exist. So this is kind of mental image in other terms. You see how many people, actually in this case 57, watch the same artifact from the same spot, okay? In order to have the protocol in place, you have to stay exactly on the same position. And the dark red shows the main region of interest. At the very end, you see that we have result particularly interesting in the way we see empathy between us and the faces of the statues. And this is the difference between men and women. And here, see the level of engagement here, and the region of visual region of interest is more, say, visible in the women category, but particularly in the way we track other eyes. This is very much close to the way we see others, other humans. So the fact that there are statues don't change, in my opinion, the fact that we tend to have a sort of eye tracking, eye empathy, or eye synchronization, even if we know this is an artifact. So in quantitative terms, so the two faces and the hands are the most viewed images, region of interest. And the time is important too. So basically the observation has to consider not just the topology of the artifact, but time. And that's why we have different clusters. So it's not important just what we watch, but for how long. And this is visible, again, in the density of the average time. You see here the hands face women and face men. So that's, you see that the different dual in time or region of interest according to this chart, where you see seconds, okay? And this is the result. So the average time is particularly interesting in the case of hands. So there is kind of overlapping. It's very different in relation to faces, for example, the persistence of tracking. And then this is the case of another individual where we actually measure the emotional index. And in this case, you see in the slide, so the points are colored in green if the emotional index is greater than the baseline, and red otherwise. So basically, what we see here, I try to recap because it's not easy to read this chart. So at the end of this experience, so there is an initial emotional index up at the very beginning, and it starts to be down and becomes up in green in the last 5-10 seconds of observation. So we see that even in 60 seconds, there is a lot going on. So this individual has a lot of different perspective. And at the end, and this could be also a wish for the future, we move the virtual reality to the hospital, and we work with patients with stroke. And we still have to process all this data, but what is important here was the engagement of all these people, which actually stuck in the hospital with only 3 hours of therapy a day, and they have no chance to do anything else. And virtual reality became for them a way to see a museum they couldn't visit or not in that condition. And what is a very fascinating, non-surprising, but fascinating, the people in a wheelchair with the same motor skills, walking in the VR. Basically, no difference. Motor skills are intact. That's why the embodiment is here, not in the arm, not in the legs, not in the rest of the body. So the brain was engaging, actually, in experience, and the experience was interestingly different from patients with verbal issues rather than with motor motor skills issues and so on. So this was just an experiment, but according to the group of psychology working with us, was particularly effective, very beneficial. And I left that session remembering the last question of one of them asking, "Are you guys providing a cure for us?" Of course not. But that was just the beginning of the discussion about art and as a therapy. And then I conclude with my last chapter, I say today, which is how to connect computing brains to artificial intelligence. Again, I don't pretend to be the first and the one. I'm just I want to share some experiment to be useful, and particularly in our field. Well, there is a lot of AI now in media. There's a lot of discussion, ethical and non-ethical, and so on. Well, first of all, I like to give you the complexity of the problem, because if you don't see the complexity, it's hard to have an opinion. On this picture, you see that there are different platforms and tools we have available today. Text to image, text to videos, text to audio, text to text, text to 3D, text to code, and so on. And on the right, you can see the platform. Some of them are commercial, some of them are open source, and so on. Short story, this is OpenAI DALL-E launched in 2021. This is the Elon Musk initiative. Then Google, Imagen, and Midjourney. But more important than second part is the Google Dream Fusion, OpenAI's Point-E. Some of them are commercial or semi-commercial. So they give you credits. When your credits are over, you have to pay a fee. Okay. The open source platform I'm using and my team is using is named Stable Diffusion. It's located physically in San Francisco, and was the first AI open source available online, at least recently. There was a startup behind Stable Diffusion, and then finally they licensed the algorithm for general use later on. So my work and work of my team is mostly based on machine learning on personal computer. So we didn't do anything online. It was running, of course, the algorithm goes online because, well, that's the power. 400 billion of images available. That's the thing, right? That's the challenge. So the term Stable Diffusion, this is important also for, let's say, the theoretical, philosophical discussion that perhaps at the end, is because of the, it wants to design a process of gradually integration of machine learning models and so on. So this is the idea. And then we can, of course, train the model, test the model, and, of course, discuss interpretations. This is the so-called fine-tuning Stable Diffusion. So means that because it's open source, user could do more than running the model on their own hardware, so they could modify the model and so on. Particularly, this is the sequence we use. Teach the model new subject like a person, an image, or video, and so on. Fine-tune models generate images in a certain style. You can make something more accurate if you teach the model to do that. Fine-tune the model with better quality images or higher quality, textual description to improve overall the output of the model, and so on. Anything else, of course. And then you generate images. The images can be 10, 20, 13 in very few minutes, or it can be even 1,000 if it takes more computing power. And essentially, this turns Stable Diffusion from a generic model into 1,000, in theory, endless, because this is about computing power. This is more in detail the work done by my colleagues trim booth, textual inversion, LoRa, and hypernetwork. I can talk this maybe later. I don't want to spend time on this, but if you are not familiar with stable diffusion, this is, I think, a very quick, easy example. So we see the pirate ship here, stable diffusion algorithm, and then we say text to image pirate ship. You have a pirate ship coming, right? In the more technically, the other example, cosmic beast, text encoder, image information creator, so the neural network here, image decoder, and then a new image. Usually they come out at 512 by 512, unless you want a higher resolution. Then we go to archaeological case study. Does this make sense in archaeology? Yes, no, how? Well, my first case study is about Etruscan tumuli, which is actually an interesting topic because it can be related to other archaeological shapes. You know, tumuli is not just in Etruscan archaeology. In this case, it was the fine-tuning was based on 21 images. I see that, particularly in this case, we decided different typologies of, look, this was just an experiment to test the algorithm, so we don't have to see yet a higher level of interpretation, but it's important. So each image was tagged with a scripted test. So basically, you teach the algorithm how to deal with textual analysis or textual prompts. Then, in this case, was use a unique identifier in order to have this kind of cluster of images related to that specific simulation. Then we ran a few different experiments with different training steps. So, for example, how many times each training image is shown to the model to learn. And then the optimal resulting model were selected by trial and error based on the quality of output and the observation point. This is the second step of the work. So there is another platform called The Forum, where you can create videos like this, intersecting landscape visualization with single monument. So basically, you here use a neural network in order to multiply basically the visualization of tumuli with different prompts. You can see use the landscape, Tuscan landscape, Etruscan roads, Etruscan cemeteries, and finally, you have also some people you can get and generate automatically by the algorithm in this case. So you see at the very bottom, so the prompt, which is based on Etruscan tumulus mound, entrance, ancient family, walking near it, realistic color. There's a negative part of the prompt too. So you see the complexity of this. This is the semantics of that. Can we imagine the semantics where we can work on even more sophisticated taxonomy, or perhaps we can see the evolution of tumuli from the Neolithic perhaps to other period of times. And you see here is the same, the forum with 25 images, and then the generation of different tumuli based on with the same idea. The visualization by prompt analysis and the intersection or comparative work with aerial view of the landscape and so on, which is based on aerial photo coming from Etruscan cemeteries and so on. In other terms, what is the point for me is the multiplication of knowledge by simulation, because the more we generate, this is called generative archaeology or generative AI, so the fact that you have different visualization coming from there. I can talk maybe later about that more in detail, but this is my excavation, so this is another experiment coming from very empirical elements. So this is a Roman building, and with details that you can see here, travertine floor, there bricks and opera incerta in that specific case, and marble tiles with coming from Asia Minor. So it's a very interesting decoration. Okay, this is just the premise, but at the end I use the prompt Roman sanctuary, which is actually what I think is travertine floor, Nishiwi statue 3D render. It's not the end, of course, but it can be to me, a sort of comparative work when I want to visualize something. I don't know yet, because the level of uncertainty remains equally difficult. But I need to visualize something. I don't know the statue, so I don't care about which statues, but I want to see statues in place with niches, with a travertine fall reflecting like that, and perhaps one day, the sanctuary cannot be just one, but more than one. In this case, the experiment is based on the humanization of Roman portrait or Roman statues. This is the Emperor Trajan. This use depth technology, so called technically depth to image methods, again stable diffusion. We started with an image of the Emperor Trajan, real from Munich here, 512 depth model. Interface tool launched by the Web UI, which is actually the computer PC platform. And then we use different cycle of depth to image processing. And you see the result here. Okay, so the point is the portrait of Trajan is an authentic artifact, but it's not an authentic reconstruction. I'm saying that we don't see the colors, we don't see the eyes, we don't see the original as it was. So in other terms, in order to have something back to the Roman, we have to create something which is closer to our imagination. And that's one of the possible example, of course, to use. Then I use another case study, which is an Etruscan stela with inscription, very difficult to read. This is a very recent work, so we just started with 3D laser scanning. The stela is in a museum now in Milano, in Italy. And I start to train here the algorithm for reading the inscription. This is particularly interesting, I guess, for epigraphy or in general for difficult readings, where actually some sign or markers can be accidental, but others can be letters, right? Actually are letters because there is an inscription there. So in this case, I start to do some training, and you see that then the algorithm start to recognize letters. So it's just the very beginning of my work, but I think it will be very promising because we cannot actually approach that with just empirical observation, because after 2 years of study, all the specialists are stuck with the same interpretation. They don't see other letters. So the digital model, very high-res digital model, created a new opportunity to read again description, and perhaps artificial intelligence can help us to give a sense to the Etruscan sentence, which is more difficult, of course. And then we come to the end of this presentation with this.
I've seen things you people wouldn't believe.
Thank you.
For over 100 years, the OI has been a leading research center for the study of ancient Middle Eastern civilizations. Join us in uncovering the past and learn about the beginnings of our lives as humans together. Become a member by visiting oi.uchicago.edu/member.